Great, thank you for the introduction, and thank you for having me here. It's been great to come out to Chur, and also to see all of the amazing work going on in the NLP space in Switzerland. So today I'm going to talk about online handwriting recognition in the vision language models age. And this is joint work with the team, and in particular with Claudio's team, who's sitting here. So in case I say anything wrong, he can correct me immediately, please. Thank you. So I was already introduced. I'm not going to rehash what was said. One thing is, that we are an applied research team. We do a lot of product-inspired research. And so we work closely with teams in YouTube and ads and cloud and Android and so on, and try to build out core technologies that are useful to our users and to our products. So one thing is, you might see here, I mentioned media understanding and generation. I have a confession to make, which is I'm actually a computer vision guy. And so I was thinking, like, what am I going to say at the SwissText conference as a computer vision guy? And then I was thinking more and more. And, I think with these new models and this new kind of age that we're going through, what I realized is that we don't really have NLP guys, people and vision people and whatnot. All of these things are merging together into single models, large multimodal models. And a lot of NLP people are doing vision work, and vision people are doing NLP work, and all these things are kind of coming together, which I find super exciting, and I think it's a direction that brings together these communities in a really good way, and definitely mutually beneficial. So that said, I do have some text things to talk about, because part of our team does handwriting recognition, which obviously is text. And it's very much at the intersection of computer vision and text. We're obviously trying to recognize text, but we have different input modalities, right? So like images of text or online handwriting and so on. So in this talk, I'll start by doing an intro to online handwriting recognition and digital ink recognition. And then I'll talk about some very hot off-the-press work, which is essentially 2 papers that we recently published. And I know Claudio gave a talk here last year, and I'm sure he was talking about our fancy RNN-based models and all these other things. And I guess he was asked, yeah, but what about LLMs? And he said, hold on, so I'm here to talk about what we're doing with LLMs a year later. And it's been a fun year. So the 2 things I'll talk about is digital ink representations and connections to vision language models. The second one is digital ink de-rendering, or kind of going the opposite way and going from images to digital ink. And I'll provide some closing thoughts, and we should have plenty of time for questions. All right, so quick sort of intro to what it is we're talking about here. When we talk about online handwriting input or hand-drawn input, what are we talking about? And usually we talk about offline and online. So offline is basically an image of some handwritten text or some printed text in this case. And that's basically the problem of optical character recognition, or OCR. Digital ink understanding, or online handwriting recognition, is a completely different modality, because here what we have is actually a time series, right? We have somebody writing, and you get 2D points, time, potentially pressure and other things, but basically it's a time series that we're using as input. So two different ways to look at handwriting recognition, and 2 different modalities. So you might ask, why are we interested in online handwriting recognition? And the reason is that it's a very natural way to input text on certain form factors. So if you have an Android phone, actually, you can even try it on your phone through the Gboard handwriting layout, which is all the way at the end over there. If you're trying to input something on a watch, the keyboard is obviously impractical there, and it's much more natural to just, jot things down on the watch. Other things are Keep, for example, note-taking. Google Translate is another place to use it. In particular, some scripts and languages are less convenient to use with a keyboard and much more convenient to just, write down the characters. Other types of input tools across products, and of course, when you're talking about online handwriting input, it doesn't necessarily have to be text. It can be, diagrams, schemas, equations, all sorts of other things that are much easier to draw than to try to input with a mouse or a keyboard. One cool one here, cars as well don't really have keyboards or practical ways to input. That's another place where we can use our models to input text. So, I guess Claudio was here probably presenting our fantastic models last year. And, when we're doing text recognition, at some point we're kind of like, it's been around for a while. It works pretty well. It has very low error rates. Are we done, basically? Can we move on to another problem? Is it solved? And in the meantime, we're obviously going through this technological transformation with large models. How do we connect the two? How do we go to the next level in terms of our capabilities? And so really here is how do we bring handwriting and digital ink understanding and all this kind of free-form interaction capabilities to these models directly. So I guess I'm trying to say we're not done yet. So this morning, Louis, in one of his last slides, was saying, there are these future areas, and one of them was multimodal models. And that's a space that we're passionate about. And one example of these are the vision language models. So this is the Pali architecture. It's a model that we released a year or two ago. And what this enables to is go from an LLM, which is basically a text in, text out model, to a multimodal model now that can do text in, image in, and text out. And so the way this is done is the text goes in as it would an LLM. And then the image can be basically encoded through what we call a vision transformer to get some tokens, and then we can feed all of that into a transformer encoder, through a transformer decoder, and decode some text. And this is really cool because it's using all the same sort of building blocks as LLMs do, but now we can pull in images, which is another modality, and get sort of all the goodies and all the knowledge that's baked into the LLM models. So the reason we like this also is because it's super flexible, right? It's just text, image, input, text, output. And then anything you can represent with text, anything you can represent with image, you throw it in and get some text output. So what this model is doing, for example, is generating the alt text, so basically a description of the image. But because it's building on top of these LLMs, you can say, answer in Chinese, or generate the text in Hindi, or in English, or anything else. And the model is able to do these things. But now, because it's also LLM-based and it has this flexible architecture, you can also ask it to count stuff in the image or do all sorts of different tasks, always with this same architecture, the same building blocks, everything is the same infra and so on. And so this is really powerful. And in fact, there's even work that shows that you can do things like object detection. So, because it's text output, and we know that these LLMs can not just output natural language, but they can output code and whatever you feel like, whatever you train it to do. You can do things like object detection, where you say, okay, I want you to output text, but those texts should be the coordinates of bounding boxes from objects. And that goes to show how flexible this framework is, and that's why we like it. So I put a link there. There are more details on Pali online. So now the question we ask is, how does this connect back to online handwriting recognition? It's a slightly different modality. How can we kind of build on top of these classic building blocks and get all the goodies? So just as a reminder, the raw input is basically a time series of 2D points, right? So you can use that as input, the raw input, which is more kind of an end-to-end learning approach, or you can represent it in different ways. Things like Bezier splines or triplets of cubic polynomials, etc. And yeah, so basically, up to the engineer to figure out what the right way to approach. But basically, there are different options for how to feed that modality in. So again, like I said earlier, these models can solve many different tasks. And these are some of the tasks that we're interested in solving. So things like classification, I draw something, you tell me what it is. Obviously text reading, which is kind of our bread and butter thing. But then you can imagine also other things like I was saying earlier, diagrams, math, music sheets, so many more. And math is an interesting one. I know how painful it is to input math equations in any other way than handwriting, so that's one that I personally like a lot. So why connect to online handwriting with VLMs? I touched on this a bit earlier. Basically, we want to use the knowledge baked into VLMs. And then the other thing is using common off-the-shelf models, methods, infrastructure, hardware. There's so much momentum behind these models that taking advantage of all of that requires to have sort of an infrastructure that we can plug together. All the research on fine-tuning, parameter-efficient tuning, all these things become available to us as well. Multitask capabilities, I mentioned earlier the different tasks that we wanted to solve, but these models are very good at solving different tasks. And that's also something that we wanted to kind of take advantage. And then finally, they're also really good at things like zero-shot, few-shot capabilities, and all these other things. So really what we're trying to say is, we gain a lot from taking a modality and basically tokenizing it in a way that it can feed into some of these large models, and then you get the benefit from all of the knowledge baked in. And I guess maybe one of the things that I'm trying to say here is that we're doing it with online handwriting, but you can imagine doing it with many different modalities. And that's how we see kind of these large multimodal models being more and more capable. So here are some example data sets that we use. Again, with handwriting, there are different types, drawings, text, math, different languages, different scripts, and all these other things. And so there are a number of data sets out there that we use to benchmark our models across some of these dimensions. All right, so now we get into, we have this digital ink. We have these models like the Pali architecture, for example, where you have a text input, you have an image input that goes through a vision transformer, and that gets merged into an encoder, then a decoder, and we can decode some text. So now we have this new modality. How do we throw it in as well, right? And it turns out there are many different ways you can do that. And we've explored a number of them, two in particular. and also combinations, which I think is interesting. So the first thing you can do is just take this online handwritten equation, for example, and just render it into an image and then just throw it in. Now you have an image, you have text, you just throw it in, vision transformer, and your problem solved. But the reality is when you do that, you're losing some information. You know, I said we had things like the time series, you know, the speed of the stroke, all these other things. And when you do the first version, you lose a lot of information, which reduces the quality of your model. So the next thing you can do is start playing around with the intensity of the pixels when you render this ink, right? You can say, actually, the intensity will be the time. So, you know, as you're going through, the pixel intensity changes. And if you want to do more, you can also add time plus distance rendering, and now you have an RGB image that you're throwing in. And now you're keeping a lot more of the original information that was in the handwritten stroke. So you can see already there a couple of different options, mostly adding more and more information and experimentation to see what works best. And then you think you're done. This is a simple problem, but you know, in our field, nothing is ever simple. So then you can say, okay, but how do I render this in an image? Do I cut it? Do I do multiple images? Do I put everything in one line? Do I render in 2 lines? Do I zoom in? Do I do that? And so again, here, there are a lot of different options for how we convert this handwritten text into an image such that we can feed it into, for example, a Pali-like model. So the first way was just to render as an image, and then we have the image modality, and you know, it's kind of well understood, and we have the models for that. The second thing we can do is say, okay, we have this time series, this 2D time series, can we tokenize that or encode that directly, and then feed those tokens into our large model? So we explored that as well, and what you see in the beginning is basically the original time series. Then you have to decide, you know, how much are we going to sample from here? Like, you know, how many points do we need? So there's some sort of time sampling. And, you know, why we do that is because we don't want too many tokens as input, right? There's always a balance between how detailed your input is and how, you know, how many tokens you can afford. So once we've done that, then we do scale normalization, then discretization, and then represents the points as in terms of their coordinates and the difference between the previous point and the current point. And what's cool is that this can just be text. So, you know, now we have another text input. And again, we're using the same thing, text input, image input, through our encoder decoder and our text output. So I think, yeah, one of the main things that I'm saying here is that actually even this sort of basic text plus image type architecture is actually super flexible to solve many, many different things. So this is just a slide to talk about the effect of sampling and kind of, so you get a feel for what kind of information you're losing as you're decreasing your sampling rate, or increasing your sampling rate in this case. So yeah, basically, like I said, you know, we had this modality, we figured out ways to convert them to images or to text, and then we can use all these standard methods. You know, Pali is one that goes through an encoder decoder, but there are other models like Palmi and others. Essentially, as long as you have this kind of input and output, you can feed these into these models and train them, taking advantage of all of the setup that's already there for these kind of models. So here are some results. I said my favorite one was math, so there's the maths. So the top line is the input digital ink. Then we have the ground truth. And now, like I said, we can play around. Do we use the image representation of the ink? Do we use this ink sort of tokenized or the ink as text approach, or do we use both? And interestingly, using both yields the best results, which means likely each one of those representations that we designed to turn the ink into an image or to turn the ink into text is kind of losing something. And when we throw the two together, that's when the model can really sort of perform at its best because it's retaining most of the information. Some more results. So these are different models. Most of these are more sort of what I would call classic models, aside from the two bottom ones, which are the ones that I just described. So what you can see here, and it's on these three data sets, math handwriting, the Vietnamese one, and the deep writing. And what you see is that we actually gain in performance even over the state-of-the-art models for most of them, aside from the MyScript model, which is specifically trained for Vietnamese. And so this is the one where we're not quite performing as well, but we're extremely close and also not training a language-specific model. Yeah, maybe one other thing that I'll mention here is that we have the input type there, image versus ink plus image. And what we see generally is that the ink representation does better than the image representation, but when we go through these poly-type architectures, the best we do is when we combine them together. All right, so this is kind of my takeaways for the first part of the presentation, which is the representation includes relative discretized coordinates as text and rendered ink with time distance as image, and putting those two together provides the model with the most information to work best. The other thing is VLMs profit from multimodal inputs, and the image is particularly important in cases where the ink's text representation doesn't fit into context length. So with the image, we have a fixed set of tokens, depending on how we set up our vision transformer. The text representation of the ink can become very long if there's a long ink. And this seems to help the model with the image representation. Again, the approach is compatible with parameter efficient tuning as well as fine tuning. There's literally nothing custom in this, which I think is one of the cool kind of, the cool thing of these model architectures is that essentially with a little bit of massaging on the inputs, you can feed in pretty much any modality. And VLMs are good at multitasking. We should be able to solve, mainstream tasks. So, what we're interested in doing is, for example, I showed 3 data sets, but there are many more and many different tasks, including classification and other things. And we think this type of setup gives us the multitasking ability to solve all these different problems with a single model, instead of having many different specialized models. So what else can we do with these architectures now that we're playing around in the vision language model space? How about digitizing pen and paper notes and teaching these models to write? Can we teach an LLM to handwrite? That would be pretty cool. So actually, I'm curious, do many people take notes on tablets here? Anybody? A few? Yeah, a few. Now, how about on paper? A lot more, okay. Yeah, me too, actually. Or a bit of both. But imagine you could, do all your work on your usual pen and paper, and then take a picture and digitize all the ink and then do search, whatever, all the things that you want to do. So I thought that's a cool use case. Can we teach a VLM to do that as well? And the answer is sure, why not? So the problem definition here is, let's say you have a photo of handwriting that's offline, it's just a picture, and you want to extract a digital version of the online handwriting from the picture. And I mean not just OCR. I mean actually knowing the strokes that were used to write this content, right? So that's the problem definition. And again, how can we turn this into an input and output with the same VLM structure that we've been using since the beginning? So ideally, we want to train a model that locates the handwriting, differentiates from the background, noise, or any other things, and then writes geometrically and semantically consistent inks in a natural way. So the input is something like that, a picture of handwritten text, and the output is the model saying, oh, okay, if that's what was written, then this is what the online handwriting looks like. So it's really kind of learning how to write based on these pictures. So again, photo of the individual word, add a textual prompt if you like, because we have this image plus text input and text output. Throw it through our model, which we call Insight, and then get a sequence of ink tokens. So again, I've already been through this, but just to kind of remind folks, digital ink consists of strokes, which in turn consists of coordinates. So we have these time series of 2D data points. We want to normalize them, sample the points, separate the tokens for XY coordinates. And this gives something like this, which is actually extremely similar to what I was describing earlier, again, showing sort of how sort of easy and generalizable this is. So in this case, we have a stroke, which is an S. We have a token that describes the beginning of the sequence. Then we have tokens that represent the positions of the points across. Of course, this is sampled. And then we have a text label, which is, this is the letter S, right? And then there's a fixed size canvas. So again, this is extremely similar to the previous approach that I was describing, but applied to a different problem. And also, it's flipped around because now these digital ink strokes are the output of the model, not the input of the model anymore, right? So, as with everything in machine learning or AI, we need to start with some data. We didn't really have data, but there are many things we can do to create this data. And so, all of the data that we used to train the previous recognizers, well, all we need to do here is flip it around. So we can take our digital inks, render them into images, and then train the model to reproduce the original digital ink. And so these are some examples of images that we created from our digital ink strokes. And then, of course, we can do data augmentation and throw all sorts of colors and backgrounds and things to make the model more robust. Now, again, like the earlier approach, oftentimes we see that adding, different representations of the input modality or throwing in many different tasks together that are related actually helps the model perform even on the single task. So we created all these different tasks that are, for example, derender with text, where the input is the image, and the prompt is derender the ink with the character, so the model knows the character, and then the output is the strokes, right? The second one that we call vanilla derender is basically the image as input and just say derender the ink. I don't care what it says. I just want the strokes, right? Oh, there's another task. And there's a third task that can be recognized in derender. So now give me the image input and tell me what the text is and give me the strokes. The next one can be just recognition. So like, here's an image, tell me what the text is. And that can be the synthetic data or any real data. And I guess what I'm saying here is throwing in all these different task mixtures seems to help the model perform across and on each individual task better. So this should be familiar by now. You know, and I think this is, you know, if there's one point that I'm trying to make here, is that these core sort of basic architectures are super generalizable and can solve many different tasks as long as you can fit the right sort of inputs, text and image, for example, and you have the data to train it to be able to learn kind of what type of task you're doing. But really my point here is that of all these different things that we've seen today, we're always based on this same kind of architecture. So again, here, the input is an image. We have a task, derender the ink, or derender the ink board if I know what the text is, or recognize and derender. These are all the different tasks that are thrown in. Run the image part through the VIT, go through the encoder, decoder, get the ink tokens out, and then render them and get your text output. So we've done a bunch of ablation studies. And these are, again, across a number of data sets. And one of the models that we train, small I. I guess the main point here is we're showing that all of these different tasks and teaching the model to do related tasks and so on is actually helping a lot. So like, if we ask the model to derender and understand the text, it actually does a lot better on the task. And when we take some of those others out, we don't do as well. So really like throwing in, you know, related tasks and other synthetic data and other things, all these things are helping the model improve in its quality. And you can see that probably the biggest one is the data augmentation. So, you know, I think synthetic data and data augmentation and so on is an interesting area to push more in. Right, so just quickly the TLDR on this table. The inference task matters. Data augmentation is actually kind of necessary in this case. You know, adding recognition and de-rendering tasks, it improves the quality. So even though it's not exactly the task we wanted to solve, it actually helps the model to do the de-rendering task. And the impact of frozen VIT in multitask training is important as well. So whether you know which parts of this architecture do you freeze and not and so on is also an important aspect. So inference tasks, again, I've already been through most of the points here. Again, we have the different tasks, right? This is more what I wanted to show. These are examples of inputs and outputs, and across sort of the vanilla approach, the using recognition approach, and there's a third thing that you could actually do, which is to run your OCR engine to tell the model what the text is you're trying to de-render. And this gives you an idea of what the quality differences look like. So obviously the model is doing, the more information it has, the better it does, which I guess is no big surprise. Yeah. So here are some more cool results. Handwritten, printed text. We feel like we've basically taught the model to write, which is kind of cool, and that there could be some interesting use cases for that, and works surprisingly well. I wanted to touch base quickly on evaluation. I know that we heard a lot about evaluation today, and I think, looking at accuracy metrics and F1 scores and other things is one thing, but it's often not telling you the whole story. And so, oftentimes going through human evaluation is a way to really understand what's going on. So we set up a human eval pipeline where we have the input image, the de-rendered ink, and then the de-rendered ink overlaid on top of the original image. And then we ask people, is the digital ink a reasonable tracing of the input image? Yes, it's good, it's okay, but has some small errors, or it's bad. And the other one is, could this digital ink have been produced by a human? Does it look human made or not? And this is what we got back. So is the digital ink a reasonable tracing of the input image? We have actual human traced data, and then we have 3 model variants, 2 small ones and a larger one. And what we can see is that we get up to 87% of reasonable inks with our largest model. And to the other question, could this digital ink have been traced by a human? Again, there we get to 67% realistic ones. So this is perhaps not a big surprise to anybody or a fancy conclusion here, but yet again, things get better with more data and with larger models, and that's true in this case as well. And I'm sure you guys are aware of that. So this, I think, is actually an interesting one. We talked about synthetic data and how data augmentation, synthetic data, and other things like that can really help improve models. So with this one, what we said is we have tons of images of handwritten text. Can we use our model to de-render them to an online handwriting data set, right, to a time series, and then train a recognizer on that? And this is where it's pretty cool, because if we compare the top one, so that's with the original, the second one is using the de-rendered ones, which is actually worse than the real data. But when we combine the two, we can get even better. And so it's this kind of combination of true high-quality data with additional synthetic data that gets us to the best results. And we often find that it's that combination of high-quality data plus synthetic augmented data that brings us to the quality we're looking for. Here are some more results on different kinds of text and so on. Again, different languages, cursive handwriting, other things, yeah. And so, yeah, with that, you could take a picture of your notes and digitize them properly. So this is another, it was a surprise to us, kind of. So the model was trained only on text. And we thought, why don't we just throw some drawings at it and see what it does? And surprisingly, it's not perfect, but it starts to have an idea of how things are drawn as well, which we found was a really interesting capability. And got us excited to pursue that direction as well. All right. So some closing thoughts. I think I made the point several times, but basically we created new digital ink tokenizers that enable vision language models to understand and generate online handwriting. And I think for me, what's really important here is using this approach enables to use really all the standard building blocks of, off-the-shelf models, off-the-shelf architectures, using all of the mainstream approaches, using potentially hardware and other things. It enables us to do fine-tuning, parameter-efficient tuning, all of that. And, if you think of it, what we were doing before was training very specialized RNN architectures that were hyper-optimized for online handwriting recognition, and, years and years spent optimizing these things. And here in a very short period of time, we can, just render the ink in images, come up with a fairly simple representation to convert the strokes to text, throw them into a standard, Pali type architecture, and essentially reach state-of-the-art results, or very close to, that had taken years and years and years of research to optimize against. And I think that really shows kind of how powerful these models are, how flexible they are, how multitask they are. And I think is, if we can do it with digital ink, then you can imagine we could do it with many other kinds of modalities. And I think that's how we'll start getting a lot of these different modalities into these models as well. So that kind of goes, VLMs can extend to new modalities as long as we have decent tokenizers or ways that we can feed them in. And the last point is kind of using multiple representation in this case helps the model. So ink as images, ink as strokes. I think probably it's because as we're converting this digital ink to these different representations, we're probably losing a bit here and there. And by putting them both back in, we kind of get that information back. So the last thing I wanted to mention is that we believe that enabling these vision language models to interpret and generate digital ink is going to enable new ways to interact with them in a seamless way. So, we talked about inputs on different form factors, phones, tablets, watches, cars, etc. We think that, strokes and drawing and things like that is a very natural way to interact, right? Also, if you think of other use cases like education and so on, if you're, the way I would explain something to somebody if we were sitting down at a desk would be to draw and to underline things and point to things and so on. And so we think there's a huge opportunity for these models to not just understand, for example, speech and images and so on, but also to understand, handwritten and free-form input. And with that thought, I'll stop there.
Thank you, Jesse. This has been very interesting. Are there any questions?
I think you were first over there, yeah. 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 All right, so the first question was about speed. So as I showed, we can encode speed in an RGB channel in the image. The other thing is in the text representation, you get sort of the speed through the delta of the points, right? Because we encode consecutive points that are uniformly sampled. So, all right? Yeah, yeah. But yeah, we can also do without speed. There are different approaches there. Yeah, yeah. Your second was about personalization. I think there, of course, because we're using standard architectures, anything that you can do with an LLM is possible here in terms of tuning and other types of approaches, federated learning and so on. we're just using standard toolkit at this point. Yeah. I think there was you first there.
Hi, I'm sure it's not the first time I've heard this question. I'm just genuinely curious. So there is like a glaring huge dual use risk with generating sure. What kinds of mitigations exist or activities?
You mean for generating a certain person's handwriting?
Yeah.
Yeah. So we obviously don't do that. Yeah. So we're obviously, careful, and we work with the right teams to make sure that's not possible for a given person. And also in terms of the data that we use and so on, we're careful with it. So it's obviously something that we take seriously and that we, mitigate for sure.
Okay, so you use a limited
At this point, this is a research model, basically. Yeah. I think you were first. Okay, go ahead.
Do you ever try sketch generation? So like given an image and some prompt generates a sketch, so
We haven't done that directly, but it's a good idea. Yeah.
I was curious, so this is a fine-tuning approach, right? So could you move that task into pre-training? So you have like interleaved, the standard image text stuff, and you also have the handwriting information. Or is it just the tokenizers that you put to expand this way?
No, I think you probably could. Again, what our goal was to do here is just to kind of convert our problem into all the standard, tooling and setup. And so this is one way of doing it. But once you've done that, you end up with ink as image or ink as text, and you can do many things once you have an image or text, and all of the toolkit is kind of available. Yeah. So right now, these are research explorations. And yeah, we're looking at it from that angle at the moment, which is basically, can we go through these standard building blocks to, treat this modality just like we treat sort of the more mainstream ones? And it seems like we can. And yeah, that's where we are at the moment. Go ahead. Sorry. Yeah. Yeah. So basically, what you're referring to is more like in an editing mode where you can strike things out or write new things and so on. Yeah, I mean, basically, I think gestures and things like that are something that are it's the same input modality. And so, we saw that things generalize pretty well, and so strike-throughs and stuff like that are things that are on the table for sure.
I was just curious, in the human evaluation, like, do you have any examples of when the hardest types of text to categorize, like doctors?
I could imagine that would be the case. I don't think we had any of that in our sets. I'm not specifically familiar if there are any certain set of verticals or types of things that are working better than others. Yeah, it'd be interesting to look at doctors' prescriptions. Yeah.
So you showed some examples where you have very short tokens, so one single word or something like that.
Mm-hmm.
Whereas the language model usually has a long sequence of text.
Yeah.
Do you do anything particular to handle single words, or maybe some sequence of digits which doesn't have any context at all?
We're not doing anything particular. This Pali architecture that we were building on top is usually shorter input and shorter output. That's what the model is kind of trained for, and we build on top of that. So we're not doing fancy stuff there. Any more questions?
I think there's one question.
Sorry, yes. Yeah. Yeah, that's a good question. I think, you know, we know that we need a lot of data for some of these models. And generating that, also even not directly the task we're training for, but tasks that are close to, but not exactly the same helps. I think we're just helping the model to generalize better. And that's why it's, you know, less overfitting and so on. And I think that's probably the main reason. Yeah.
Have you considered using the same approach on another kind of time series data? For example, audio or EEG?
So, yes, I mean, there's obviously a whole body of work around audio input. It's not exactly the same tokenizers, and I think on the audio side, there's often a lot more processing going on top. It's a bit of different modality, so there are different ways of tokenizing audio. Those are more sort of specialized tokenizers rather than what I showed here, which are more sort of quite straightforward and generic. Yeah. Yeah. I'm not sure I got the question. So you're saying that the ones that were rated as computer generated were actually human. So you're saying, were those so bad that people would... I haven't looked into all the details, to be honest. Yeah, but I would say pretty bad. Yeah, I don't know. Yeah, Claudio agrees. Yeah, yeah.
Good, excellent.
Right.
Thanks a lot for this very interesting talk.
Thank you.
I also want to thank you.
Thank you very much.
Dr.